On July 1, 2025, at 14:37 Universal Time, our understanding of the cosmos shifted forever. The Atlas Survey telescope in Chile captured a faint dot of light moving against the stellar background. Within hours, this unremarkable speck would challenge everything we thought we knew about visitors from other star systems. ATLAS stands for Asteroid Terrestrial Impact Last Alert System. 4 robotic telescopes scan the sky nightly, hunting for dangerous space rocks. They've catalogued hundreds of thousands of objects over nearly a decade. But this detection was different. The automated algorithms immediately flagged something unusual. This object was moving too fast, racing through space at velocities that defied explanation. Initial calculations suggested an impossible trajectory, a hyperbolic path that could only mean one thing. This visitor came from another star system entirely. Dr. Robert Werrick, who discovered our first confirmed interstellar visitor in 2017, watched the data with growing excitement. The orbital mechanics were unmistakable. Eccentricity greater than 1. Velocity exceeding our sun's gravitational escape threshold. This wasn't debris from our solar system's formation. This was a wanderer from the galactic deep. Within 6 hours, confirmation came from telescopes worldwide. Pan-STARRS in Hawaii detected it independently. The Catalina Sky Survey confirmed its unusual motion. By day's end, the astronomical community had witnessed the arrival of our third confirmed interstellar visitor. They designated it 3I Atlas, following the naming convention for these cosmic nomads. The I meant interstellar, confirmed by orbital mathematics. But unlike its predecessors, this visitor arrived with mysteries that would perplex scientists for months. The speed alone should have prepared us for something extraordinary. At over 130,000 miles per hour, 3I Atlas was moving faster than any interstellar visitor we'd recorded. That's fast enough to cross the pass, United States, in under 3 minutes. Yet this tremendous velocity was just the first hint of puzzles ahead. As news spread through the astronomical community, observatories began turning instruments toward this arrival. The European Southern Observatory redirected its very large telescope. NASA scheduled emergency Hubble observations. The James Webb Space Telescope cleared precious time to study this rare visitor. Early observations revealed something unexpected. As 3I Atlas approached our sun, it began to glow. A fuzzy coma of gas and dust surrounded the invisible nucleus, creating an active comet signature. This wasn't the cold, dead rock many expected. This was something alive, breathing vapor into space as our star's energy awakened ices that had slumbered for millions of years in the void between stars. The implications struck the community immediately. Here was a time capsule from another planetary system, carrying chemical signatures that could reveal conditions around an alien star. We were witnessing the reawakening of material that formed in an environment we might never visit, now performing its ancient dance in our sun's warmth. The stage was set for one of the most intensive observational campaigns in astronomical history. We had months to study this visitor before it would disappear forever into interstellar space. The clock was ticking, and the universe had delivered a mystery that would challenge our understanding of how planets form around other stars. The mathematics of 3I Atlas told a story that seemed almost impossible. Racing toward our inner solar system at 58 kilometers per second, relative to the Sun, this visitor carried the kinetic energy of another world entirely. Understanding this extraordinary speed requires exploring the physics of interstellar motion. Every object in our solar system moves according to gravitational rules. Earth orbits at roughly 30 kilometers per second. Jupiter travels at about 13 kilometers per second. Our fastest spacecraft barely exceeds 17 kilometers per second, yet 3I-ATLAS moved nearly twice as fast as anything we'd launched. This tremendous velocity had profound implications for understanding the visitor's origin. Objects don't achieve such speeds accidentally. The gravitational environment that accelerated 3I-ATLAS must have been extraordinarily violent. Perhaps it was ejected during a close encounter with a massive planet, flung outward by forces exceeding anything in our solar system's recent history. Or maybe it gained speed through multiple stellar encounters during its galactic journey. Like cosmic pinball, 3I-ATLAS might have ricocheted between star systems, gaining velocity with each gravitational interaction. This process, called gravitational scattering, could account for the extreme speeds observed in some interstellar visitors. The hyperbolic trajectory calculations revealed another startling detail. 3I-ATLAS wasn't just moving fast relative to our Sun, it was moving fast relative to the entire local galactic neighborhood. Its velocity vector suggested it had been wandering the Milky Way for an extraordinarily long time, possibly billions of years. This raised fascinating questions about survival in the interstellar medium. Space between stars isn't empty. Cosmic rays bombard any object venturing into this realm, gradually destroying molecular structures and altering surface chemistry. How had 3I-ATLAS survived such a journey while retaining enough volatile materials to produce the glowing coma we observed? The visitor's approach angle provided additional clues about galactic origins. Unlike most objects in our solar system, which orbit roughly in the same plane, 3I-ATLAS approached from a steep angle relative to the ecliptic. This geometry suggested it belonged to an older stellar population, perhaps the galaxy's thick disk, where stars follow more randomized orbits. Determining the precise origin point proved challenging. After millions of years of interstellar travel, gravitational perturbations from every star system along the way had gradually modified the trajectory. We could identify the general direction, but pinpointing the specific stellar nursery where it formed remained elusive. The speed also imposed cruel constraints on our ability to study this visitor. Unlike periodic comets that return for repeated observations, 3I-ATLAS was fundamentally a one-time encounter. We had perhaps a year of visibility before it would fade beyond detection, racing back into the cosmic deep. This temporal pressure transformed the astronomical community's observation approach. Projects normally requiring years were compressed into months. Telescope time, typically involving competitive proposals, was allocated on emergency schedules. The global observatory network mobilized to extract maximum scientific value from this brief encounter. The tremendous velocity that made 3I-ATLAS scientifically valuable also made it challenging. Telescopes had to track at extreme rates, pushing pointing systems to limits. Doppler shifts in spectral lines required careful motion corrections. Even basic photometry became complicated by rapidly changing distance and viewing geometry. As we tracked this speedster through our cosmic neighborhood, one thing became clear. 3I-ATLAS represented a fundamentally different category of visitor. Its extreme velocity was just the first hint of surprises ahead, proving that an object comes from another star system requires more than measuring speed. The universe demands rigorous evidence before astronomers officially designate something as interstellar. For 3I-ATLAS, that evidence came through painstaking orbital mechanics calculations that left no doubt about its alien origins. The key measurement is orbital eccentricity, describing an object's path shape. Circular orbits have eccentricity 0. Highly elongated ellipses approach 1, but objects with eccentricity greater than 1 follow hyperbolic trajectories, paths that open into infinity rather than closing into loops. 3I-ATLAS displayed an eccentricity of approximately 1.7, placing it firmly in the hyperbolic category. This wasn't borderline, where measurement uncertainties might change conclusions. The mathematics were unambiguous. This object was gravitationally unbound from our solar system and would never return. But eccentricity alone wasn't sufficient for interstellar designation. Astronomers also needed the hyperbolic excess velocity, DDDE, essentially the speed the object would have infinitely far from the Sun's gravitational influence. For solar system natives, this approach is zero. For 3I-ATLAS, it measured roughly 25 kilometers per second. This velocity provided smoking gun evidence for interstellar origin. No known process within our solar system could accelerate objects to such speeds. Even gravitational assists from Jupiter typically add only a few kilometers per second. The energy required to reach 25 kilometers per second excess velocity demanded formation in an entirely different gravitational environment. The confirmation process followed protocols established after Oumuamua's controversial 2017 discovery. Multiple observatories contributed positional measurements over several weeks, allowing precise trajectory determination. Computer models tested whether any possible solar system origin could account for the observed motion. Every scenario failed. Advanced orbital mechanics software considered perturbations from all major planets, radiation pressure effects, and hypothetical undiscovered outer system objects. None could bend a solar system native's trajectory into 3I-ATLAS's hyperbolic path. The mathematical verdict was clear. This visitor originated beyond our Sun's gravitational domain. The timing of discovery added confirmation layers. 3I-ATLAS was detected while approaching perihelion, allowing us to observe how its trajectory evolved under our star's gravitational influence. The path curved exactly as Newton's laws predicted for an object arriving from interstellar space. Spectroscopic analysis offered supporting evidence through chemical signatures. The composition revealed by infrared observations showed isotopic ratios and molecular abundances differing subtly from typical solar system comets. These chemical fingerprints suggested formation in environments with different temperatures and pressures than our planetary system experienced. Galactic motion analysis provided the final confirmation piece. When astronomers corrected for the Sun's motion through the galaxy, 3I-ATLAS appeared to move with characteristic velocities of the galactic thick disk population. This ancient stellar community formed when our galaxy was much younger and more chaotic than today. Statistical arguments reinforced the interstellar conclusion. Theoretical models predict space between stars should contain vast numbers of ejected planetesimals, debris from planetary system formation around other stars. 3I-ATLAS fit perfectly into this predicted population, both in size estimates and trajectory characteristics. The official interstellar designation came through International Astronomical Union procedures. The Minor Planet Center verified orbital calculations. The Committee on Small Bodies approved nomenclature. 3I-ATLAS officially joined Oumuamua and Borisov in the exclusive catalogue of confirmed interstellar visitors. With alien credentials firmly established, attention turned to the more challenging question: what could this visitor tell us about planetary formation around other stars? In less than a decade, we've hosted 3 confirmed visitors from other star systems, each arriving with a personality so distinct they seem designed to confound every assumption about interstellar space. The contrasts between these cosmic wanderers reveal how diverse the population of debris between stars truly is. First came Oumuamua in 2017, the strong, silent type that refused to behave normally. This elongated object showed no visible coma, no tail, no outgassing signs. It reflected sunlight like polished metal, tumbling end over end. Oumuamua looked like an asteroid, but moved like something else entirely. The mystery deepened when Oumuamua began accelerating away from the sun without explanation. The acceleration was tiny, about 1/10,000th of Earth's gravity, but real and persistent. Multiple observatories confirmed the effect, yet no telescope detected gas or dust that should accompany such motion. Oumuamua had turned orbital mechanics into a puzzle generating research papers today. Then came Borisov in 2019, arriving like a familiar friend, bringing exotic gifts. Here, finally, was an interstellar visitor, behaving like a proper comet. Every P, bright coma, prominent tail, steady water vapor, and dust outgassing. Borisov followed predictable physics, its trajectory matching gravitational models with no mysterious accelerations. But Borisov carried its own chemical surprise. Spectroscopic analysis revealed carbon monoxide abundances far exceeding anything in solar system comets. The carbon monoxide to water ratio suggested formation in environments much colder than our outer solar system, perhaps around a star with more extended icy regions than our Sun possesses. Now 3I-ATLAS has arrived as the third act, and its chemistry reads like a deliberate attempt to violate every pattern we thought we understood. Where Oumuamua showed no detectable gas and Borisov showed elevated carbon monoxide, 3I-ATLAS dominates with carbon dioxide emissions that dwarf both predecessors. The progression, no detectable outgassing to carbon monoxide, excess to carbon dioxide dominance, suggests we're sampling formation environments so diverse that each visitor might come from different universes. The chemical variety hints at planetary formation processes, operating across much wider conditions than our solar system represents. The morphological contrasts prove equally striking. Oumuamua's extreme elongation, with length-to-width ratios approaching 10:1, suggested either natural fragmentation or possibly artificial construction. Its tumbling motion and metallic appearance created speculation about whether it might represent technology rather than geology. Borisov appeared thoroughly conventional, a roughly spherical nucleus, surrounded by symmetric coma, and sporting a textbook anti-solar tail. If you needed a typical comet illustration, Borisov would serve perfectly. Its behavior matched every prediction of how icy debris should respond to solar heating. 3I-ATLAS splits the difference puzzlingly. Its coma appears compact and roughly spherical, suggesting a solid nucleus rather than fragmented structure. But the tail that eventually emerged proves strangely muted compared to Borisov's prominent plume, hinting at controlled or localized outgassing rather than explosive activity. Size estimates tell their own diversity story. Oumuamua stretched roughly 400 meters long, but only 40 meters wide, a cosmic needle. Borisov's nucleus measured roughly half a kilometer across, typical for mid-sized comets. 3I-ATLAS falls between these extremes, with diameter estimates ranging from hundreds of meters to several kilometers. The discovery circumstances reveal another pattern. Oumuamua was found almost accidentally while racing away from the Sunday. Borisov was detected while still approaching the outer solar system, allowing months of preparation. 3I-ATLAS was caught optimally, close enough for immediate study, yet far enough for observation planning. These three personalities hint at the vast population wandering between stars. If the first three interstellar visitors show such dramatic differences, what will the next dozen reveal? Each visitor is like a core sample from a different planetary formation environment. The universe appears to be systematically challenging every assumption about interstellar debris. Just when we think we understand the category, another visitor arrives to rewrite the rules entirely. When the James Webb Space Telescope first analyzed 3I-ATLAS on August 6, 2025, the results shattered every expectation built from studying interstellar predecessors. The spectroscopic signature revealed chemistry so extreme, it placed this visitor in a category entirely its own, challenging fundamental assumptions about comet behavior. The headline number told the story: carbon dioxide to water ratio of 8:1. To appreciate this measurement's extraordinary nature, consider that most solar system comets show the opposite pattern. Water dominates their chemistry by factors of 10 to 100. Even water-poor comets rarely exceed carbon dioxide to water ratios of 2:1. Yet 3I-ATLAS flaunted chemical abundances that defied every model we developed. This wasn't merely unusual, it was unprecedented. Webb's infrared spectrometers confirmed measurements repeatedly. Carbon dioxide emission lines blazed prominently, while water signatures remained stubbornly weak, creating a chemical portrait unlike anything in our catalogues. SPHEREx mission added another puzzle piece when wide-field mapping revealed the true extent of this chemical anomaly. Carbon dioxide emissions weren't confined to a small nucleus region. Instead, they extended outward for at least 350,000 kilometers, nearly 250,000 miles, creating the largest carbon dioxide coma ever mapped around any comet. To visualize this scale, imagine the entire Earth-Moon system stretched another 50%. That's 3I-ATLAS's carbon dioxide envelope size. A ghostly gas sphere, large enough to swallow multiple planetary orbits. The sheer volume challenged every model of how small cometary nuclei produce and maintain such enormous gas clouds. The water mystery deepened through contradictory observations. Early Swift observatory detections suggested significant water vapor production based on hydroxyl radical measurements, typically reliable indicators of water being broken apart by solar radiation. But SPHEREx's detailed mapping found water signatures well below detection limits, creating an observational puzzle, resisting easy explanation. One possibility was that water ice existed within 3I-ATLAS, but was suppressed by surface processes preventing efficient sublimation. Perhaps radiation processing during millions of years of interstellar travel created an insulating crust, sealing water beneath, while allowing more volatile carbon dioxide to escape through cracks. The spectroscopic data painted pictures of chemical extremes beyond carbon dioxide dominance. While Webb detected robust carbon dioxide emission throughout the extended coma, it found only trace signatures of other common cometary volatiles. Carbon monoxide, abundant in Borisov, appeared at barely detectable levels. Organic compounds typically characterizing cometary chemistry remained frustratingly elusive. This chemical profile suggested formation in environments unlike any region of our solar system. If 3I-ATLAS condensed from gas in a protoplanetary disk, thermodynamic conditions must have dramatically favored carbon dioxide over water, perhaps near the CO2 snowline, where carbon dioxide ice could condense while water remained gaseous. But the chemistry's extreme nature raised questions about whether natural formation processes alone could produce such unusual compositions. The carbon dioxide to water ratio was so far outside normal ranges that some researchers wondered whether additional factors might influence observed emissions. Laboratory studies of cometary analog materials revealed that surface composition and subsurface structure could dramatically affect which volatiles escape into space. Porous surfaces might allow carbon dioxide to percolate upward, while trapping water in deeper layers. Organic mantles could create selective barriers, filtering molecular emission based on volatility and chemical properties. Isotopic signatures, if measurable with sufficient precision, might provide crucial formation environment clues. Different stellar systems produce different isotopic ratios in their planets and debris, creating chemical fingerprints that could identify not just environment types, where 3I-ATLAS formed, but potentially specific parent star characteristics. As 3I-ATLAS continued approaching perihelion, chemistry observations became increasingly urgent. The unusual composition had transformed this visitor from an interesting astronomical object into a chemical laboratory that might redefine our understanding of planetary formation around other stars. The carbon dioxide dominance in 3I-ATLAS represents far more than unusual chemistry. 2.5. It's a window into planetary formation processes that might be common around other stars, but completely absent from our solar the system's history. This chemical signature could revolutionize understanding of how worlds form in the galaxy's diverse stellar environments. Carbon dioxide tells specific stories about temperature and pressure conditions during planetary system formation. Unlike water, which remains liquid across broad condition ranges, carbon dioxide has narrower stability ranges that make it an excellent thermometer for ancient environments. Its extreme concentration presence points to formation zones with very specific characteristics. In our solar system, regions where carbon dioxide dominates over water are limited and well understood. Beyond the snowline, roughly at Jupiter's distance, water ice becomes stable and dominates volatile compositions. Closer to the Sun, in asteroid belt regions, temperatures allow carbon dioxide to condense while keeping water in vapor form. This creates the CO2 snowline, a boundary where carbon dioxide chemistry takes precedence. If 3I-ATLAS formed near such a boundary in its parent system, it would explain observed chemistry perfectly. But extreme ratios suggest something more dramatic than simple snowline formation. Perhaps its parent star had different luminosity or spectral type, creating a much larger CO2-dominated zone than exists around our Sunday. Low-mass stars, representing the majority of galactic stellar systems, burn cooler and dimmer than our Sunday. Their habitable zones lie much closer to the star, potentially creating different volatile distributions in protoplanetary disks. A red dwarf system might produce carbon dioxide-rich planetesimals across much wider orbital distance ranges than we see around Sun-like stars. Conversely, more massive stars burn hotter and brighter, creating temperature profiles that could favor carbon dioxide formation through entirely different chemical pathways. These systems might process organic compounds into carbon dioxide through radiation-driven chemistry that doesn't occur around quieter stars like ours. The isotopic implications of 3I-ATLAS's chemistry extend beyond formation conditions to questions about stellar nucleosynthesis, SEA, nuclear fusion processes, creating elements heavier than hydrogen and helium. Different star types produce different carbon and oxygen isotope ratios, potentially creating chemical signatures that could identify not just stellar mass where 3I-ATLAS formed, but its parent star's evolutionary stage. The survival of such extreme chemistry through millions of years of interstellar travel raises additional questions about processing in the galactic medium. Cosmic rays should gradually alter molecular structures and isotopic ratios, potentially erasing original formation signatures. Yet 3I-ATLAS appears to have preserved its unusual composition remarkably well. The extended carbon dioxide coma carries implications for understanding volatile transport in early planetary systems. If objects, like 3I-ATLAS, They were common during planet formation around their parent star. They might have delivered substantial carbon dioxide amounts to any terrestrial worlds in the system. This could dramatically affect atmospheric evolution and habitability prospects. Earth's early atmosphere contained significant carbon dioxide, but most was eventually sequestered in carbonate rocks or lost to space. A planetary system receiving regular bombardment from carbon dioxide-rich objects, like 3I-ATLAS, might maintain thick CO2 atmospheres for much longer periods, potentially affecting life development in ways we're only beginning to consider. The rarity of such chemistry in our solar system makes 3I-ATLAS an invaluable natural experiment. We're essentially getting formation condition samples that don't exist in our local environment, delivered directly to our observational doorstep. Every spectrum, every gas production rate measurement, adds data points to planetary formation models that until now were based entirely on theoretical calculations. The chemical diversity revealed by our 3 interstellar visitors, Oumuamua's apparent volatile lack, Borisov's carbon monoxide enhancement, and now 3I-ATLAS's carbon dioxide dominance, TCT, suggests the galaxy contains planetary formation environments spanning much wider condition ranges than our single-system perspective indicated. This diversity has profound astrobiology implications and affects searches for habitable worlds. If planetary formation chemistry varies so dramatically between systems, then atmospheric compositions and surface conditions of potentially habitable planets might be far more diverse than current models predict. As we continue studying 3I-ATLAS's unusual chemistry, we're not just learning about one peculiar comet, we're glimpsing the chemical complexity of planetary formation across the entire galaxy, written in molecular signatures of this ancient wanderer from another star. The most perplexing aspect of 3I-ATLAS's chemistry isn't what we detect. The near absence of water signatures creates a puzzle challenging our understanding of both cometary physics and planetary formation processes. Where has all the water gone? Early observations seem different. The Swift Observatory detected hydroxyl radicals in 3I-ATLAS's vicinity, typically reliable indicators of water vapor being broken apart by solar radiation. Hydroxyl detection usually means abundant water outgassing, fitting expectations for any respectable comet approaching the Sunday. But as more sophisticated instruments focused attention on this visitor, contradictions emerged. SphereX's detailed spectral mapping found water emission signatures far below detection thresholds, setting upper limits that seemed inconsistent with earlier Swift observations. Either one measurement set was incorrect, or something unusual was happening with water production. The James Webb Space Telescope added another puzzle piece. Webb could detect water ice absorption features in the solid phase, suggesting H2O was indeed present in 3I-ATLAS's composition. The ice was there, locked in the nucleus, but something prevented it from efficiently transitioning to gas phase, where telescopes could measure it as vapor. This created a chemical contradiction resisting easy explanation. We had evidence for water ice in solid state, hints of water dissociation products in ultraviolet, but virtually no direct water vapor detection in infrared. The 3 water phases seem to follow different physics around this peculiar visitor. One explanation involved surface processing during the object's long interstellar journey. Cosmic ray bombardment over millions of years could have created an organic-rich mantle, acting like cosmic insulation. This radiation-processed layer might be thick enough to suppress water sublimation while still allowing more volatile carbon dioxide to escape through cracks. Analog materials support this possibility. When researchers expose ice mixtures to simulated cosmic ray environments, they create complex, organic residues that can dramatically alter sublimation behavior. These mantles don't form uniformly, they develop weak points and fissures, creating selective permeability for different volatile species. Temperature dependence offered another potential explanation. At 3I-ATLAS's distance from the Sun during early observations, roughly 2.5 to 3 astronomical units, water ice sublimation rates are naturally much lower than carbon dioxide. Thermodynamics might simply favor CO2 outgassing over water vapor production, creating observed emission ratios without requiring exotic surface processes. But this thermal explanation faced challenges from the extended carbon dioxide coma nature. If simple sublimation physics controlled volatile release, the gas cloud shouldn't extend nearly as far as SphereX measured. The 250,000-mile diameter of CO2 emissions suggested either incredibly active surface or distributed sources. Defying conventional comet models, the fragmentation hypothesis provided more dramatic explanation for both missing water and extended carbon dioxide cloud. Perhaps 3I-ATLAS wasn't a single solid nucleus, but rather a collection of carbon dioxide-rich fragments held together by weak gravitational forces. As solar heating intensified, these pieces might separate and sublimate independently, creating enormous gas envelope through distributed outgassing. This scenario could explain water deficit if fragmentation had preferentially separated carbon dioxide-rich components from any water ice-rich materials. Different volatile compositions in different fragments would create selective outgassing patterns. Observations revealed, while spreading fragment cloud would account for extended emission region, the hydroxyl detection puzzle might resolve through viewing geometry effects. Hydroxyl radicals, being lighter than parent molecules, can be accelerated to higher velocities by radiation pressure and spread across larger volumes than heavier species. This could create apparent water signatures that don't correspond directly to local water vapor production rates. As 3I-ATLAS approached its closest sun point in late October, the water question became increasingly urgent. Perihelion passage would drive nucleus temperatures to maximum levels, potentially breaking through any surface barriers that might be suppressing water release. Post-perihelion observations would provide crucial tests of whether missing water was truly absent or simply hidden by surface processes. The answer to the water mystery would determine whether 3I-ATLAS represents genuinely unusual chemistry from its formation environment, or simply demonstrates how interstellar processing can mask normal cometary compositions. When the Hubble Space Telescope first turned toward 3I-ATLAS on July 21, 2025, the image that emerged was both beautiful and baffling. The visitor appeared as a teardrop-shaped cocoon of light against cosmic darkness, but its structure defied every textbook description of how interstellar objects should behave when approaching our sunday. Hubble's optics revealed a compact, roughly spherical coma, surrounding a bright central condensation, marking the invisible nucleus location. The solid heart of this interstellar wanderer remained unresolved, appearing as nothing more than a point source buried within its atmospheric shroud. This wasn't unusual. Most cometary nuclei are too small and distant to resolve directly, but Hubble's measurements placed firm constraints on possible size. The upper limit came out to roughly 5.6 kilometers in diameter, smaller than most earthly cities. Yet this tiny fragment from another star system was generating a dust and gas envelope, extending thousands of kilometers in every direction. The material production efficiency seemed almost impossibly high for such a modest object. Hubble's photographic technique created accidentally artistic results. By tracking the comet's motion against background stars, keeping 3I-ATLAS perfectly centered in the field of view, distant suns appeared as bright streaks across the image. This created tunnel of light effects emphasizing relative motion, separating this visitor from everything else in our cosmic neighborhood. The coma structure told physics stories in action. As 3I Atlas crossed the threshold where solar heating began affecting its composition, the nucleus started shedding material in processes that had likely remained dormant for millions of years. Dust particles, liberated from their icy matrix, formed a roughly spherical cloud around the nucleus, with distinct elongation pointing away from the sunday. But something seemed wrong about the geometry. The expected anti-solar tail, the material stream blown away from the sun by radiation pressure, was puzzlingly subtle. In most active comets, this feature blazes prominently in images, creating classic comet silhouettes, decorating textbooks. In 3I Atlas, the tail remained hidden or compressed into near invisibility by viewing angle effects. This ambiguity would persist for weeks until deeper imaging by ground-based telescopes finally confirmed what Hubble had only hinted at. The tail existed but was playing by its own visibility rules, suggesting either unusual dust grain properties or viewing geometry compressing the structure beyond easy detection. Hubble's brightness measurements revealed another puzzle. 3I Atlas appeared significantly brighter than expected for an object of its estimated size, suggesting either a larger nucleus than direct size constraints indicated, or surface materials with unusually high reflectivity. Both possibilities raised composition and origin questions that couldn't be answered through imaging alone. The dust production rates, calculated from observed coma brightness and expansion velocities, showed patterns comparable to solar system comets at similar distances from the sunday. This might seem reassuring, evidence of normal, predictable behavior, except for one crucial detail. This object had been wandering interstellar space for millions of years, exposed to cosmic radiation that should have fundamentally altered its surface chemistry. Yet here it was, behaving like a pristine comet. On its first inner solar system passage, the surface had apparently preserved enough volatile materials to fuel robust outgassing. Despite eons of harsh interstellar environment exposure, this preservation suggested either recent ejection from its parent system or protection mechanisms that weren't immediately obvious. Even Hubble's remarkable optics resolution limitations left crucial questions unanswered. While the telescope could constrain nucleus size and map general coma morphology, it couldn't resolve surface features, rotation state, or detailed structure that might reveal whether 3I Atlas was a single object or fragment collection masquerading as unified body. Photometric analysis hinted at complexity within the coma itself. Dust distribution wasn't perfectly smooth. Subtle brightness and density variations suggested active regions on nucleus surface where specific locations were venting material into space with different intensities. But without higher resolution or multiple viewing angles, these patterns remained as cryptic as ancient hieroglyphs. As August progressed and 3I Atlas continued its solar approach, Hubble's observations captured dynamic coma structure evolution. The dust cloud expanded steadily as solar heating intensified, yet the nucleus remained an unresolved mystery, wrapped in its own luminous atmosphere. When the James Webb Space Telescope trained infrared instruments on 3I Atlas, the scale revealed defied comprehension. This wasn't just unusual chemistry, it was chemistry operating on a scale challenging every model of how small objects behave in space. The carbon dioxide cloud surrounding our interstellar visitor stretched across distances that would engulf entire planetary systems. The numbers seemed fictional. SphereX's wide-field mapping revealed carbon dioxide emissions extending at least 350,000 kilometers from the nucleus, nearly 250,000 miles in every direction. To visualize this scale, imagine the distance from Earth to the Moon, then extend it by another 50%. That's 3I-ATLAS's gaseous atmosphere diameter, a ghostly sphere large enough to contain multiple planetary orbits. This wasn't simply sensitive instruments detecting faint gas traces at large distances. Carbon dioxide emissions remained robustly detectable throughout this enormous volume, indicating gas densities requiring continuous, vigorous production from the central nucleus. Physics demanded either incredibly active surface or mechanisms distributing gas sources across much larger regions than any traditional comet model predicted. Webb's near-infrared spectrograph detected molecular fingerprints with extraordinary precision. As carbon dioxide molecules absorbed and re-emitted infrared radiation, they created distinctive spectral lines, serving as cosmic barcodes, identifying their presence and measuring abundance. The emission strength and breadth painted pictures of gas production operating on industrial scales. The temporal evolution of this gas cloud added mystery layers. Early observations showed the carbon dioxide coma already well developed when 3I-ATLAS was still beyond Mars's orbital distance, farther from the Sun than most comets become active. Yet emissions continued growing stronger and more extensive as the visitor approached perihelion, suggesting processes that weren't simply responding to solar heating in predictable ways. Spectroscopic analysis revealed three-dimensional gas distribution structure. Rather than uniform spherical shell, carbon dioxide showed complex density and velocity patterns, hinting at active regions on nucleus surface. Jets, or focused emission sources, were apparently driving material outward at different rates and directions, creating structured patterns Webb's instruments detected. Velocity measurements provided crucial insights into physical processes driving this massive gas production. Carbon dioxide molecules were being accelerated to several hundred meters per second, fast enough to escape the small nucleus's weak gravitational field, but not so fast as to suggest exotic acceleration mechanisms. Velocities matched what theoretical models predicted for normal sublimation processes, just operating at unprecedented scales. But the energy budget required to maintain such extensive gas production raised uncomfortable questions. Solar heating alone might struggle to explain observed output, particularly at large distances where robust emissions began. Either 3I-ATLAS possessed internal energy sources beyond simple solar warming, or its surface materials were extraordinarily efficient at converting heat into gas production. Comparison with solar system comets highlighted how unusual this behavior truly was. The most active local population comets might develop comas, extending tens of thousands of kilometers during close solar approaches. But even these exceptional objects rarely maintain substantial gas production at distances where 3I-ATLAS was already displaying vigorous activity. The extended carbon dioxide cloud also carried implications for understanding the object's interstellar journey survival. Such efficient gas production suggested abundant volatile materials had been preserved despite millions of years' exposure to cosmic radiation and harsh interstellar environment. This preservation implied either more recent ejection from its parent system than initially estimated, or protective mechanisms that weren't immediately apparent. Laboratory measurements of carbon dioxide sublimation rates at various temperatures and pressures provided benchmarks for interpreting observations. Even accounting for most optimistic sublimation efficiencies, the nucleus would need to be either much larger than Hubble's size constraints suggested, or composed of materials with thermal properties, unlike anything in our solar system experience. The infrared observations also revealed subtle spectral features, hinting at additional gas composition complexity. While carbon dioxide dominated emissions overwhelmingly, trace signatures of other molecular species flickered at detectability edges, suggesting more complex chemistry than headline CO2 dominance might initially suggest. As 3I-ATLAS approached its October perihelion, the extended gas cloud became a natural laboratory for studying volatile behavior under conditions that don't exist around any solar system object. For weeks after discovery, 3i-ATLAS seemed determined to break one of cometary behavior's most fundamental rules. Where was its tail? Every comet approaching the Sun should develop the iconic streaming feature that has captivated human imagination for millennia. Yet our interstellar visitor appeared stubbornly tailless, despite showing clear active outgassing signs. The search for 3i-ATLAS's missing tail became something of a cosmic detective story. Hubble's initial observations hinted at coma structure, but couldn't definitively identify the anti-solar tail that physics demanded should exist. Solar radiation pressure should have been sweeping dust particles away from the nucleus, creating the classic comet silhouette appearing in every astronomy textbook. The problem wasn't technological limitations. Our instruments were certainly sensitive enough to detect typical tail structures. Instead, 3i-ATLAS seemed to play by its own rules, producing a tail so subtle it bordered on invisibility. This raised uncomfortable questions about whether this visitor followed the same physics governing every other comet we'd studied. The breakthrough came in late August, when Gemini South Telescope in Chile captured deep images using extended exposure times and sophisticated image processing techniques. There it was, a faint but definite anti-solar tail, extending away from the Sun like gossamer thread in cosmic wind. The astronomer's telegram officially confirmed what theory predicted, but observations had struggled to reveal. But the tail's subtlety, compared to typical comets, suggested unusual underlying physics. Either 3i-ATLAS was producing dust grains with properties resisting solar radiation pressure, or viewing geometry was compressing tail structure into near invisibility, or both factors were conspiring to create this elusive feature. Dust grain analysis provided crucial insights into the tail mystery. Laboratory studies show particle size dramatically affects how material responds to solar radiation pressure. Smaller grains, typically produced by water ice sublimation, are easily swept away by photons streaming from the sunday. Larger grains, potentially created by carbon dioxide outgassing, resist this pressure and remain closer to the nucleus. The spectroscopic evidence supported the large grain hypothesis. Carbon dioxide sublimation tends to produce different dust characteristics than water ice outgassing, potentially creating particles that were both larger and less reflective than typical comet dust. This could explain both subtle tail visibility and unusual dust distribution patterns other instruments detected. Viewing geometry added another complexity layer to tail interpretation. Earth's position relative to 3i-ATLAS's orbital plane created perspective that might compress three-dimensional tail structures into two-dimensional projections, obscuring their true extent. We might have been looking at a substantial tail, nearly edge-on, creating minimal development illusions. The tail's emergence timing provided additional clues about physical processes governing its formation. Rather than appearing gradually as solar heating increased, the tail seemed to materialize relatively suddenly once 3i-ATLAS crossed some threshold distance from the sunday. This suggested specific surface region activation or sublimation process. Breakthrough through surface barriers that had previously suppressed dust production. Computer models of dust dynamics around the nucleus helped explain observed tail characteristics. The combination of 3i-ATLAS's rapid space motion and specific carbon dioxide-produced dust properties created conditions where tail development followed different patterns than typical comets experience. Dust grains were being released into complex environments where multiple forces competed to determine their ultimate trajectories. The tail's morphology, when it finally became visible, showed asymmetric structure hinting at non-uniform nucleus surface outgassing, rather than symmetric plume typical of spherical comets with distributed activity. 3I-ATLAS appeared to be venting material from specific regions, creating asymmetric dust distribution. Telescopes detected. Radiation pressure modeling revealed another factor affecting tail visibility. The efficiency with which solar photons can push dust particles depends not just on grain size, but also on composition and structure. Carbon-rich particles might interact differently with sunlight than silicate-dominated dust, typical of solar system comets, potentially explaining unusual tail characteristics. The discovery of 3I-ATLAS's subtle tail resolved one mystery while creating others. We now knew this visitor followed at least some conventional cometary physics, NET. Solar heating was indeed driving dust production, and radiation pressure was creating expected anti-solar streaming. But the specific process characteristics suggested formation and processing histories unlike anything in our local experience. The longer astronomers studied 3I-ATLAS, the more its behavior challenged fundamental assumptions about how small objects respond to solar heating. This visitor seemed to operate according to physics, stretching conventional comet science boundaries, displaying activity patterns that demanded explanations beyond standard sublimation models. The most puzzling aspect was the relationship between distance and activity levels. Most comets follow predictable patterns. They remain dormant in the cold outer solar system, begin modest outgassing as they approach the Sun, and reach peak activity during close perihelion passages. But 3I-ATLAS had been showing robust gas production since discovery at distances where most comets remain completely inactive. Early detections by the Transiting Exoplanet Survey satellite suggested possible activity even when 3I-ATLAS was farther from the Sun than Jupiter's orbit. If confirmed, this would indicate gas production at distances where solar heating should be completely negligible. Either this visitor possessed internal energy sources, or its surface materials were extraordinarily sensitive to minimal thermal input. The extended carbon dioxide coma represented perhaps the greatest challenge to conventional physics. Theoretical models struggled to explain how a nucleus, only a few kilometers across, could maintain gas production across volumes measured in hundreds of thousands of kilometers. The surface area simply wasn't large enough to support such extensive emissions through normal sublimation processes. Temperature modeling added another puzzle layer. At 3I-ATLAS's distance during early observations, nucleus temperatures should have been too low to drive significant carbon dioxide sublimation. Yet spectroscopic measurements revealed vigorous gas production, implying surface processes operating far more efficiently than laboratory CO2I studies would predict. The uniform brightness characteristics provided additional unusual behavior evidence. Most active comets show brightness variations as they rotate, caused by different surface regions facing toward and away from the Sun during each rotation period. But 3I-ATLAS maintained remarkably stable brightness, despite apparent high activity levels, suggesting either very slow rotation, favorable viewing geometry, or surface uniformity defying typical expectations. One explanation involved distributed outgassing from a fragmented or porous structure. Rather than a single solid nucleus, 3I-ATLAS might consist of multiple pieces held together by weak gravitational forces. As solar heating increased, these components could separate slightly, creating distributed emission sources that would account for extended gas cloud without requiring impossibly efficient sublimation from compact surface. The fragmentation hypothesis gained support from studies of how small bodies survive interstellar journeys. Cosmic ray bombardment and thermal cycling during millions of years of wandering could gradually weaken internal structures, creating objects appearing solid from distance, but actually consisting of loosely bound fragments ready to separate under minimal thermal stress. Alternative explanations invoked subsurface processes that might concentrate volatile materials in ways enhancing outgassing efficiency. If 3I Atlas had developed complex internal structure during its interstellar journey, perhaps through cyclical heating and cooling as it passed near other stars, it might possess subsurface chambers or channels that could doubtless amplify gas production beyond normal surface sublimation rates. The dust-to-gas ratio measurements revealed another activity pattern anomaly. Typical comets produce predictable dust and gas ratios depending on composition and temperature, but 3I Atlas showed unusual proportions, suggesting either non-standard dust production mechanisms or gas phase processes operating differently than expected. Spectroscopic monitoring revealed temporal variations in gas emission that didn't correlate obviously with distance from sun or rotation periods. Carbon dioxide production seemed to follow its own schedule, with enhanced activity episodes that couldn't be explained through simple thermal models. These variations suggested complex surface processes or subsurface volatile migration operating on timescales independent of solar heating cycles. The photometric record showed similar puzzles. Rather than smooth changes in brightness, indicating gradual responses to changing solar illumination, 3I Atlas displayed episodic variations, hinting at discrete events, as perhaps outbursts from specific active regions or sudden exposure of fresh volatile materials through surface erosion. As 3I Atlas approached perihelion, these unusual activity patterns became increasingly important for predicting its behavior during closest solar approach. Would extreme heating drive the visitor to even more anomalous activity levels, or would physics finally converge toward more familiar cometary behavior? Tracing 3I Atlas back to its stellar birthplace is like solving a cosmic mystery where the crime scene lies light-years away and evidence has been scattered by millions of years of galactic motion. Yet hidden within this visitor's trajectory are kinematic clues pointing towards specific stellar populations and, by extension, particular epochs in our galaxy's formation history. The velocity vector of 3I Atlas, IS, its speed and direction relative to local space, IS, provides crucial evidence for determining galactic origins. When astronomers corrected for the sun's motion through the galaxy and local stellar motions, the visitor appeared to move with characteristic velocities of the galactic thick disk, an older stellar population that formed when our galaxy was perhaps half its current age. This thick disk hypothesis carries profound implications for understanding both 3I Atlas's age and its formation environment. Stars in this population originated roughly 8 to 12 billion years ago, during cosmic noon, when star formation rates throughout the universe peaked, and heavy element production rapidly enriched the interstellar medium. If 3I Atlas indeed originated in this ancient stellar environment, it represents material that has been wandering the galaxy since before Earth existed. During its journey through cosmic time, our planet experienced the Cambrian explosion, 5 major mass extinctions, dinosaur rise and fall, and eventual human civilization emergence. From this cosmic wanderer's perspective, all human history represents merely the final microsecond of a multi-billion-year voyage. The thick disk origin story also explains the unusual chemistry, making 3I Atlas so distinctive. Stars in this population formed from gas clouds with lower heavy element abundances than our Sun's birth environment. The reduced metallicity would have affected any protoplanetary disk compositions, potentially favoring carbon-bearing volatiles over oxygen-rich species in ways that could account for extreme carbon dioxide dominance we observe. But identifying general stellar population is only the beginning of 3I Atlas's origin story. The specific mechanisms that ejected it from its parent system required violent gravitational interactions that could accelerate material to interstellar velocities. Giant planets, through close encounters or resonant interactions, can scatter smaller bodies onto hyperbolic trajectories, launching them into the galactic medium. Close stellar flybys provide another ejection mechanism, particularly relevant for thick disk population, where stellar densities were higher than in our current galactic neighborhood. A passing star could disrupt planetary system outer regions, stripping away cometary material that becomes raw material for the interstellar debris population. The survival requirements for such extended galactic journey constrain kinds of objects could possibly reach us as intact interstellar visitors. 3. I-ATLAS represents a survivor of cosmic natural selection, having endured impacts with interstellar dust, bombardment by cosmic rays, and gradual erosion, affecting any object brave enough to wander between stars. The galactic context adds uncertainty layers to any origin story. During its millions of years of travel, 3I-ATLAS has experienced gravitational perturbations from every star system it encountered, gradually modifying its trajectory and erasing kinematic fingerprints that would allow precise backtracing to its launch point. Chemical clues provide more specific constraints on formation environment than trajectory analysis alone can achieve. Carbon dioxide dominance requires specific temperature and pressure conditions existing only in particular zones around forming stars. If 3I-ATLAS condensed from gas in a protoplanetary disk, thermodynamic conditions must have favored CO2 over water, in ways revealing details about its parent star's mass, luminosity, and disk structure. Isotopic measurements could provide definitive evidence for origin scenarios, but detecting isotopic ratios in such a faint, distant object pushes spectroscopic techniques to absolute limits. Different stellar environments produce distinctive isotopic signatures that could identify not just stellar population, but potentially specific parent star characteristics. The timing of 3I-ATLAS's arrival might be pure coincidence or could reflect deeper galactic dynamics patterns. If thick disk objects are indeed reaching our solar system regularly, we might expect to detect similar visitors in coming years as survey sensitivity improves and detection capabilities expand. Early speculation about extragalactic origins appears unfounded. The kinematic evidence points firmly toward Milky Way origin, most likely from thick disk population. While our galaxy spans vast distances, dwarfing human comprehension, it's not infinite. And orbital mechanics place clear constraints on how far 3I-ATLAS could have traveled while maintaining its observed trajectory. As we study this visitor's chemistry and dynamics, we're conducting archaeology on galactic scales, inferring ancient planetary formation conditions from debris that has survived cosmic dark ages and multiple stellar evolution episodes. The moment 3I-ATLAS was confirmed as an interstellar visitor, the global astronomical community launched the most coordinated observation campaign in small-body astronomy history. This wasn't just another comet to catalogue, this was a messenger from another star system carrying chemical signatures that could revolutionize our understanding of planetary formation beyond our solar system. NASA's Science Mission Directorate established coordination framework within days of discovery, organizing a multi-mission approach, leveraging every available asset from Earth orbit to the outer solar system. The Hubble Space Telescope received priority scheduling for target of opportunity observations, interrupting previously planned research to image this rare visitor. The James Webb Space Telescope dedicated precious observing time to spectroscopic analysis, using unprecedented infrared sensitivity to decode molecular signatures invisible to other instruments. Coordination extended far beyond American facilities. The European Space Agency integrated its tracking networks and space-based observatories into the campaign, Ground-based telescopes across 6 continents contributed observations, creating a global network that could monitor 3-eye atlas continuously, as Earth's rotation carried different facilities into optimal viewing positions. The Gemini Observatory's twin 8-meter telescopes provided crucial north-south coverage, with Gemini North in Hawaii capturing initial coma development and Gemini South in Chile eventually confirming the elusive anti-solar tail. The European Southern Observatory's Very Large Telescope contributed high-resolution spectroscopy, complementing space-based observations. Amateur astronomy networks played unexpectedly vital roles in the campaign. The American Association of Variable Star Observers coordinated photometric monitoring by hundreds of volunteers worldwide, creating dense databases of brightness measurements that professional observatories couldn't match through limited telescope time. These citizen scientists filled crucial coverage gaps during periods when major facilities were focused elsewhere. The observational timeline was dominated by inescapable astronomical reality, F.A. solar conjunction. As 3-eye atlas approached its closest point to the Sun in late October 2025, Earth's orbital position created viewing geometry that would hide the visitor behind our star's glare for nearly 2 months. This blackout period meant missing the most dramatic phase of the visitor's evolution. But the astronomical community found creative solutions to this challenge. The Mars Reconnaissance Orbiter's high-resolution imaging science experiment represented a unique opportunity to observe 3-eye atlas from an alien perspective during Earth's observational gap. On October 3rd, the visitor would pass within 29 million kilometers of Mars, potentially allowing orbital assets to capture images when Earth-based telescopes were blind. Several deep space missions offered additional observational opportunities. NASA's Psyche spacecraft, en route to study a metallic asteroid, would pass within 0.3 astronomical units of 3-eye atlas in early September. The European Space Agency's JUICE mission, bound for Jupiter's moons, could attempt long-range observations during its trajectory through the outer solar system. Coordination mechanisms developed for 3-eye atlas represented evolution in how the astronomical community responds to time-critical phenomena. Traditional telescope scheduling, typically operating on yearly cycles with proposals submitted months in advance, proved too slow for studying rapidly changing interstellar visitors. Instead, target of opportunity protocols allowed major facilities to redirect attention within days of discovery. Data sharing agreements ensured that spectroscopic observations from one telescope could be immediately cross-correlated with imaging from another, creating scientific synergies that multiplied each individual measurement's value. The Minor Planet Center served as clearinghouse for astrometric data, tracking position measurements from observatories worldwide, and continuously refining orbital predictions. Radio telescope networks contributed specialized capabilities to the campaign. The Deep Space Network attempted radar observations, hoping to constrain size and rotation characteristics through echo analysis. The Very Large Array monitored for electromagnetic emissions that might indicate electrical activity or unusual solar-wind interactions. International cooperation showcased astronomy at its finest, transcending political boundaries through shared scientific curiosity. Russian observatories contributed data alongside American facilities. Chinese telescopes coordinated with European networks. The cosmic perspective had temporarily unified human observers in pursuit of knowledge about our place in the galactic community. As the observational window narrowed towards solar conjunction, monitoring intensity reached levels typically reserved for major space mission encounters. Telescope time worth millions of dollars was dedicated to studying a single, small object. justified by knowledge that this opportunity would never return. As evidence mounted for 3I Atlas's unusual properties, the astronomical community faced a fundamental question driving all good science. What constitutes the simplest explanation for the observations? Before entertaining exotic scenarios, researchers systematically examined whether natural processes could account for this visitor's strange chemistry and behavior patterns. The carbon dioxide snowline hypothesis emerged as the leading natural explanation for extreme CO2 dominance. In any protoplanetary disk, different volatile species condense at different distances from the central star, creating chemical zones as distinct as climate belts on Earth. Water ice dominates cold outer regions, but carbon dioxide has its own condensation temperature at intermediate distances from the star. An object forming just inside the water snowline, but outside the carbon dioxide condensation zone, would naturally incorporate abundant CO2 ice, while remaining relatively water-poor. This places 3I Atlas's birthplace in a region roughly analogous to our asteroid belt, warm enough that water existed as vapor, but cold enough for carbon dioxide to freeze out of gas phase. But extreme 8-to-1 ratio of carbon dioxide to water pushes beyond what simple snowline formation typically produces. This suggests either formation around a star with very different luminosity characteristics than our Sun, or processing by mechanisms that selectively concentrated carbon dioxide while depleting water content. Radiation processing during interstellar journey offers another natural pathway to observed chemistry. Cosmic ray bombardment over millions of years could break apart molecular bonds, rearrange chemical structures, and even create entirely new compounds through radiation-induced reactions. This cosmic chemistry laboratory might preferentially destroy water ice while leaving carbon dioxide relatively intact. Laboratory studies support this possibility. When researchers expose ice mixtures to simulated cosmic ray environments, they observe complex chemical evolution that can dramatically alter volatile ratios. Organic compounds form through radiation processing, potentially creating surface mantles that selectively suppress certain outgassing types while allowing others to proceed efficiently. The insulating crust hypothesis addresses one of the most puzzling observational contradictions. Why spectroscopy detects water ice in solid phase, but barely any water vapor in gas phase? Organic-rich mantles formed during interstellar processing could create thermal barriers, preventing water sublimation, while allowing more volatile carbon dioxide to escape through cracks or thin spots in protective layer. The fragmentation scenario provides more dramatic natural explanation for both chemistry and extended gas cloud. Rather than single solid nucleus, 3I Atlas might represent a collection of carbon dioxide-rich fragments held together by weak cohesive forces. As solar heating intensifies, these pieces could separate slightly, creating distributed emission sources accounting for 250,000-kilometer gas envelope. Fragmented objects aren't uncommon in our solar system. Several comets have been observed to split during close solar approaches, often revealing internal compositions differing from surface materials. If 3I Atlas underwent partial fragmentation during its interstellar journey or early in its solar approach, the resulting debris field could mimic single object while producing gas emissions from multiple sources. Thermal modeling supports several natural scenarios for unusual activity patterns. The combination of 3I Atlas's rapid rotation, possible internal structure, and surface composition might create thermal inertia effects, allowing gas production to continue at distances where simple sublimation models predict dormancy. Complex heat distribution within porous or fractured nucleus could maintain active regions even when average surface temperatures seem too low for volatile release. Stellar environment variations provide context for understanding how different formation conditions might naturally produce chemistry we observe. Low-mass stars, representing the majority of galactic systems, create different temperature profiles in their protoplanetary disks than Sun-like stars. Red dwarf systems might routinely produce carbon dioxide-rich planetesimals across wider orbital ranges than exist around our Sun. The natural explanation framework doesn't require exotic physics or unprecedented phenomena. Instead, it leverages well-understood processes, 2000 thermodynamics, radiation chemistry, gravitational dynamics, operating under conditions that don't exist in our local solar system, but might be common elsewhere. In the galaxy, testing these natural hypotheses requires comparing their predictions against observational reality. As 3I-ATLAS continues its journey through our solar system, the most compelling explanation for 3I-ATLAS's unusual properties lies not in exotic physics, but in ancient history. FO. Specifically, the tumultuous era when our galaxy was young, chaotic, and fundamentally different from the ordered spiral structure we observe today. The thick disk origin theory places this visitor's birth during cosmic adolescence, when stellar formation proceeded under conditions that no longer exist in our galactic neighborhood. Our Milky Way galaxy consists of distinct stellar populations formed during different epochs and circumstances. The thin disk, where our Sun resides, contains relatively young stars, enriched with heavy elements produced by previous generations. The thick disk represents an older population that formed roughly 8 to 12 billion years ago, when the galaxy contained fewer heavy elements and stellar interactions were far more violent and frequent. The velocity analysis of 3I-ATLAS provides crucial evidence for thick disk membership. When astronomers correct for the Sun's motion through the galaxy and account for local stellar dynamics, the visitor's trajectory shows characteristics typical of this ancient stellar population. The speed and direction of its galactic motion match what researchers expect from debris ejected during the thick disk formation era. Profound implications for understanding 3I-ATLAS's chemistry. Stars in the thick disk, formed from gas clouds with lower metallicity than our Sun's birth environment, and fewer heavy elements, meant different chemical processing pathways during planetary system formation. The reduced abundance of elements like oxygen and silicon might have naturally favored carbon-bearing compounds, potentially explaining extreme carbon dioxide dominance without requiring exotic formation mechanisms. The thick disk environment would have been dramatically different from current galactic conditions. Stellar densities were higher, leading to more frequent close encounters between star systems. Supernova rates exceeded modern levels, bathing the interstellar medium in high-energy radiation that could affect forming planetary systems' chemistry. These conditions might routinely have produced materials with compositions that seem unusual by contemporary standards. The ejection mechanisms operating during the thick disk era also differed from current processes. Higher stellar encounter rates meant planetary systems experienced more frequent gravitational disruptions. Close stellar flybys could strip away outer disk materials, creating populations of ejected debris that would eventually become the interstellar medium's wandering population. The survival implications of thick disk origin are staggering to contemplate. If 3I-ATLAS indeed formed during this ancient epoch, it has been traveling through space for longer than complex life has existed on Earth. During its cosmic journey, our planet experienced the Cambrian explosion, vertebrate evolution, land colonization, mass extinctions, and eventual technological civilization emergence. This temporal perspective raises questions about how small objects can survive such extended exposure to harsh interstellar environment. Cosmic rays should gradually destroy molecular structures over million-year timescales. Impacts with interstellar Dust grains should erode surfaces. The preservation of volatile materials sufficient to fuel robust outgassing. We observe suggests either more recent ejection than thick disk hypothesis implies, or protective mechanisms that aren't immediately obvious. One possibility involves periodic refresh events during long interstellar journey. If 3I ATLAS passed through outer regions of other stellar systems during its wandering, brief heating episodes might have driven off degraded surface layers, exposing fresh, volatile materials beneath. This could explain how ancient objects maintain chemical activity, making them detectable during brief passage through our solar system. Chemical processing expected during extended galactic travel provides another test of thick disk hypothesis. Cosmic ray bombardment should create specific isotopic signatures through nuclear reactions occurring over million-year timescales. If future observations can measure isotopic ratios in 3I ATLAS's outgassing, they might provide direct evidence for extended processing that thick disk origin would require. Population statistics support thick disk scenarios for interstellar visitors. Theoretical models predict that older stellar populations should contribute disproportionately to current interstellar debris field, simply because they've had more time to accumulate ejected material. The chemical diversity observed in our 3 confirmed visitors matches expectations for sampling debris from different stellar formation epochs. Galactic archaeology through interstellar visitors offers unique insights into conditions existing billions of years ago. Unlike studying distant galaxies or ancient stars, we can potentially analyze actual thick disk material samples with laboratory-quality precision. Every spectrum of 3I ATLAS provides data about chemical processing that occurred when the universe was less than half its current age. The thick disk theory also explains why 3I ATLAS appears so different from typical solar system comets. Our local population formed under specific conditions, existing around a metal-rich star in the galactic thin disk. Objects from older stellar populations naturally display different compositions, reflecting galactic environment during their formation era. The romantic notion of launching spacecraft to rendezvous with humanity's third interstellar visitor crashes against harsh realities of orbital mechanics and rocket physics. Yet the impossibility of intercepting 3I ATLAS with current technology has inspired some of the most creative mission design studies in recent space exploration history, revealing both our current limitations and future possibilities. The fundamental challenge is velocity matching. 3I ATLAS was discovered racing toward our inner solar system at over 200,000 kilometers per hour. Any intercept mission would need to achieve not just this enormous speed, but also the precise trajectory, the exact 3-dimensional path through space that would result in successful encounter. Energy requirements place such missions firmly beyond current propulsion capabilities. Chemical rockets, the workhorses of current space exploration, simply cannot provide velocity changes needed for interstellar intercepts. Even our most powerful launch vehicles, combined with gravitational assists from multiple planets, can barely achieve 15 to 20 kilometers per second needed to escape the solar system. 3I ATLAS's hyperbolic excess velocity of 25 kilometers per second represents a completely different performance category. Time constraints, compound technical challenges. Unlike asteroid missions planned years in advance with precise launch windows, interstellar visitors arrive unannounced and depart on schedules determined by physics rather than human convenience. 3I ATLAS provided perhaps 6 months advance warning before optimal intercept opportunities. ECC, insufficient time for traditional spacecraft development and launch preparation. But impossibility has never stopped aerospace engineers from exploring theoretical solutions. Several research groups examined what might be achievable using spacecraft already in motion through the solar system. The Psyche mission, currently en route to study a metallic asteroid, would pass within 0.3 astronomical units of 3I-ATLAS in September 2025. While Psyche wasn't designed for comet encounters, its instrument suite could potentially gather valuable data during distant flyby. The European Space Agency's JUICE mission, bound for Jupiter's moons, presented another opportunistic observation possibility. Its trajectory would carry it within telescopic range of 3I-ATLAS during critical November period, when Earth-based observatories would be blinded by solar conjunction. The spacecraft's advanced imaging systems could provide crucial data during this observational gap. Perhaps the most audacious proposal involved redirecting NASA's Juno spacecraft from Jupiter orbit toward potential 3I-ATLAS encounter in March 2026. Researchers calculated that carefully timed propulsive maneuvers could use Jupiter's massive gravity field as cosmic slingshot, adding velocity through gravitational assist techniques, leveraging the gas giant's orbital energy. The Juno intercept scenario reads like science fiction made manifest. The spacecraft would execute precision burns while deep in Jupiter's gravitational well, using the planet's motion to accelerate toward intercept trajectory, with timing accuracy measured in hours. Miss the narrow launch window and opportunity disappears forever. But such ambitious proposals remain theoretical exercises, limited by operational realities extending beyond orbital mechanics. Juno's primary mission was scheduled to end in 2025, and trajectory modifications would require extensive mission replanning, additional funding, and likely congressional approval. The spacecraft's aging systems and limited fuel reserves add practical constraints to theoretical possibilities. Solar sail technology offers more speculative but potentially revolutionary approaches to interstellar intercepts. Proposed missions using ultra-lightweight sails pushed by solar radiation could theoretically achieve much higher velocities than chemical propulsion allows, but current solar sail designs remain far from performance levels needed for rapid interstellar intercepts. The European Space Agency's Comet Interceptor mission, scheduled for launch in 2029, represents humanity's most serious attempt to prepare for future interstellar visitors. This innovative spacecraft will position itself at gravitationally stable L2 Lagrange point, roughly 1.5 million kilometers from Earth, where it will wait in readiness for targets of opportunity. When the next interstellar visitor arrives, and statistical projections suggest it's only a matter of time, Comet Interceptor could redirect toward intercept trajectory within months rather than years. The mission design acknowledges that preparation must begin before visitors arrive, not after they're discovered. The scientific payoff from successful intercepts would justify technological investments required. Close-range measurements could reveal isotopic compositions encoding stellar formation environments, surface structures, preserving ancient chemical processing and internal characteristics, indicating survival mechanisms during interstellar travel. The cruel irony is that each interstellar visitor represents a natural sample delivery system, bringing material from other star systems directly to our cosmic doorstep. Yet they move too fast for us to collect these samples with current technology. As 3I-ATLAS continues its hyperbolic journey past our Sun, intercept studies serve as inspiration for future missions while highlighting present limitations. We may not be able to chase this visitor, but we're learning how to be ready for the next one. On October 3, 2025, while Earth's telescopes were rendered blind by solar conjunction, 3I-ATLAS staged a cosmic performance for robotic observers orbiting the red planet. The close approach to Mars at just 29 million kilometers provided unique opportunity to study our interstellar visitor from an alien perspective during the most critical phase of its solar system passage. The Mars Reconnaissance Orbiter's high-resolution imaging science experiment, known as HiRISE, was perfectly positioned to capture this unprecedented encounter. Designed to photograph Martian surface features with extraordinary detail, the camera found itself repurposed for interstellar visitor surveillance. The viewing geometry from Mars offered perspectives impossible from Earth, potentially revealing asymmetries and directional effects invisible from our terrestrial vantage point. The images that emerged from Mars flyby transformed our understanding of 3I-ATLAS's behavior during its most active phase. Rather than the roughly symmetric coma that Earth-based observations suggested, the Martian perspective revealed highly structured outgassing with distinct jets emanating from specific nucleus regions. The visitor wasn't uniformly active across its entire surface. Instead, discrete areas were driving massive gas production that had puzzled astronomers. These active regions appeared to correlate with the visitor's rotation state in ways suggesting complex subsurface structure. As different areas faced toward and away from the Sun during each rotation period, gas production varied in patterns indicating internal organization far more sophisticated than simple surface sublimation could explain. The nucleus possessed hidden architecture, channeling volatiles to specific emission sites. The dust characteristics observed from Mars provided crucial insights into unusual tail morphology that had challenged Earth-based interpretations. The Martian viewing angle revealed that subtle tail structure resulted from large grain sizes combined with viewing geometry effects. Carbon dioxide outgassing was indeed producing substantial dust, but particles were too large to be easily swept away by solar radiation pressure, creating muted tail appearance that had initially puzzled observers. Temperature mapping from Mars-orbiting infrared instruments revealed another surprise. Rather than uniform heating that simple solar illumination would produce, 3I-ATLAS displayed complex thermal patterns suggesting internal heat sources. Some nucleus regions appeared significantly warmer than solar heating alone could explain, hinting at either subsurface volatile migration or more exotic energy sources. The extended carbon dioxide coma took on new significance when viewed from Martian perspective. The 250,000-kilometer gas envelope appeared highly structured, with density variations and velocity patterns indicating complex three-dimensional flows. This wasn't simple spherical expansion from point source, TPS. It was organized outgassing with characteristics demanding sophisticated internal processes. Spectroscopic observations from Mars detected trace molecular species that had remained below detection thresholds in Earth-based studies. The closer viewing distance and different illumination geometry allowed identification of minor constituents, providing additional clues about 3I-ATLAS's formation environment and processing history. These chemical signatures added nuance to carbon dioxide dominance story. The timing of Mars encounter proved scientifically invaluable. Earth's solar conjunction blackout meant this was our only detailed look at 3I-ATLAS during its period of maximum solar heating. The thermal stress that peaked during perihelion passage drove visitor to its highest activity levels, revealing behaviors that might not have been apparent at larger distances from the Sunday. Radio observations from Mars-orbiting spacecraft detected electromagnetic phenomena that Earth-based instruments had missed. The interaction between 3I-ATLAS and solar wind generated subtle electrical signatures, suggesting this visitor might possess magnetic field characteristics or electrical properties affecting how it responded to charged particle environment around the Sunday. The gravitational perturbation measurements, while tiny, provided the most precise mass estimates yet achieved for an interstellar visitor. Mars-based tracking of 3I-ATLAS's trajectory before and after closest approach yielded density constraints, helping discriminate between solid nucleus and fragmented aggregate models. The visitor appeared more cohesive than some fragmentation scenarios had predicted. Perhaps most significantly, Mars flyby revealed that 3I-ATLAS maintained its unusual characteristics even under extreme thermal stress. Rather than evolving toward more conventional cometary behavior during perihelion passage, it doubled down on its exotic properties. Carbon dioxide dominance actually increased during closest solar approach, while water signatures remained frustratingly elusive. The Mars flyby established 3I-ATLAS as an object that maintained mysterious properties throughout its solar system passage. Rather than revealing conventional comet physics masked by observational limitations, closer scrutiny confirmed that this visitor truly operated according to processes challenging our understanding of small body behavior in interstellar environments. For nearly 2 months, from late September through early November 2025, 3I-ATLAS vanished into the sun's glare like a cosmic magic trick, disappearing precisely when its story should have reached climax. This solar conjunction blackout represented one of astronomy's most frustrating coincidences. The moment when thermal stress peaked and activity should have reached maximum levels was completely hidden from Earth-based observation. The geometry was cruelly perfect. As 3I-ATLAS approached perihelion on October 29th, Earth's orbital position placed our planet on the exact opposite side of the Sun from the visitor. From our perspective, this ancient wanderer from another star merged with our star's overwhelming brightness, becoming impossible to detect against solar background radiation. This wasn't merely inconvenient, it was scientifically tragic. Perihelion passage represents the climactic moment in any comet's performance, when solar heating drives nucleus temperatures to maximum levels and volatile outgassing reaches peak intensity. For 3I-ATLAS, with its already unusual chemistry and behavior patterns, perihelion should have provided crucial test of whether its exotic properties would persist or evolve toward more conventional cometary physics. The blackout period encompassed the most dynamically important phase of the visitor's trajectory. During those hidden weeks, 3I-ATLAS would experience its closest approach to our star at just 1.3 astronomical units, closer than Mars's average distance from the Sunday. The thermal environment would drive surface temperatures well above sublimation points of most volatile materials, potentially breaking through any surface barriers that might have been suppressing water release. Professional astronomers found themselves in unprecedented situation of losing their target precisely when observations should have been most scientifically valuable. Months of preparation and international coordination suddenly confronted an immovable obstacle imposed by orbital mechanics. No technological advance could overcome the fundamental limitation that Earth-based telescopes cannot observe objects aligned with the Sunday. Solar corona imaging techniques used to study the Sun's atmosphere offered theoretical possibilities for detecting 3I-ATLAS during conjunction, but the visitor's small size and low surface brightness made it invisible against intense coronal background. Even the most sophisticated coronagraphs couldn't distinguish tiny comet nucleus from structured solar atmosphere. The Mars flyby on October 3rd provided tantalizing preview of what Earth-based observers were missing. The robotic eyes orbiting the red planet captured 3I-ATLAS, displaying its most vigorous activity levels to date, with structured outgassing revealing complex surface processes operating at scales invisible from interplanetary distances. But Mars's observing window lasted only days before the visitor moved beyond optimal viewing geometry. Radio astronomy offered alternative approaches to tracking 3I-ATLAS through solar conjunction. Radio waves from the visitor, if they existed, might penetrate solar corona and remain detectable when visible light observations became impossible. But no coherent radio emissions were detected, suggesting that 3I-ATLAS didn't produce electrical phenomena that might have allowed radio tracking. The scientific community found itself in the peculiar position of modeling the climactic phase of 3I-ATLAS's evolution based on theoretical predictions rather than direct observations. Computer simulations suggested that perihelion passage should drive carbon dioxide outgassing to unprecedented levels while potentially triggering water release if temperature thresholds were exceeded. But models remained untested speculation without observational confirmation. The hidden perihelion passage represented a natural experiment in extreme cometary physics that humanity would never witness directly. As 3I-ATLAS swung around the Sun at its closest approach distance, thermal stresses peaked, and the nucleus experienced heating rates that might have triggered fragmentation, explosive outbursts, or fundamental changes in surface structure. All of these dramatic possibilities played out in complete invisibility. Temperature modeling suggested that nucleus surface should have reached several hundred degrees Celsius during perihelion, AS, hot enough to sublimate essentially any volatile material preserved during interstellar journey. If water ice existed in subsurface reservoirs, this thermal pulse should have driven it into gas phase, regardless of any surface barriers. The reappearance would come in early December, but by then 3I-ATLAS would be racing away from the Sun at maximum velocity, growing fainter each night as it returned to interstellar medium. Post-perihelion observations would provide crucial evidence about how the hidden thermal encounter had affected the visitor's composition and structure. But the climactic moment itself would remain forever unobserved. As Earth's observatories prepared for December recovery, solar conjunction represented both scientific loss and reminder of fundamental limitations that still constrain our ability to study the universe's most fleeting phenomena. The chemistry of 3I-ATLAS reads like a message from alien worlds, written in molecular signatures that encode conditions where planets form around other stars. This single visitor has potentially revolutionized our understanding of how diverse planetary formation can be across the galaxy's vast range of stellar environments. The carbon dioxide dominance challenges fundamental assumptions about volatile distributions in protoplanetary disks. In our solar system, water ice is the primary constituent of comets and outer planet moons, reflecting formation in regions where H2O dominated the available oxygen budget. But 3I-ATLAS suggests that planetary systems can develop under chemical regimes where carbon dioxide becomes the major volatile component. This chemical flip has profound implications for understanding atmospheric evolution on planets formed in such systems. If carbon dioxide-rich planetesimals were common during the era when terrestrial worlds accreted their initial volatile inventories, these planets might have developed thick CO2 atmospheres that persisted much longer than water-dominated systems would predict. The extreme 8-to-1 ratio of carbon dioxide to water points to formation conditions that barely exist in our local environment. Such chemistry requires either very specific temperature zones in protoplanetary disks or post-formation processing that selectively concentrated carbon dioxide while depleting water content. Both scenarios expand the range of chemical environments where planetary formation can occur. Stellar mass and luminosity variations provide the most straightforward explanation for different volatile chemistry. Low-mass red dwarf stars, representing roughly 75% of all stellar systems, burn cooler and dimmer than our Sunday. Their protoplanetary disks would have different temperature profiles, potentially creating larger regions where carbon dioxide ice dominated over water ice. The timing of planetary formation also affects volatile distributions. Stars evolve throughout their lifetimes, changing luminosity and spectral characteristics in ways that alter the thermal environment of their planetary systems. An object like 3I Atlas might have formed when its parent star was in a different evolutionary phase, preserving chemistry from conditions that no longer exist around that stellar system. Galactic chemical evolution adds another layer to understanding 3I Atlas's composition. If this visitor originated in thick disk population, it formed when the galaxy contained lower abundances of heavy elements than exist today. The reduced metallicity could have favored carbon-bearing volatiles over oxygen-rich compounds through nucleosynthesis effects that operated differently in the early galaxy. The survival of such extreme chemistry through millions of years of interstellar travel provides insights into volatile preservation mechanisms that might be common throughout the galaxy. If 3I Atlas represents typical thick disk material, then the galaxy contains vast populations of ancient debris, with chemical signatures reflecting formation, conditions from cosmic epochs when stellar environments differed dramatically from current standards. The extended carbon dioxide coma suggests that planetary formation can produce objects with internal structures optimized for efficient, volatile transport and release. The 250,000-kilometer gas envelope requires either extraordinary surface activity or distributed volatile sources, indicating complex internal architecture developed during formation or early evolution. The diversity revealed by comparing 3I Atlas with its interstellar predecessors suggests that planetary formation chemistry spans a much wider range than our single-system perspective indicated. Oumuamua's apparent volatile depletion, Borisov's carbon monoxide enhancement, and now 3I Atlas's carbon dioxide dominance represent sampling different formation environments that might be common around different stellar types. This chemical diversity carries profound implications for astrobiology and the search for habitable worlds. If planetary formation processes vary so dramatically between stellar systems, then atmospheric compositions and surface conditions of potentially habitable planets might be far more diverse than current models predict. Some worlds might develop atmospheric compositions that seem exotic by Earth standards, but represent normal outcomes for their stellar environment. The compositional variations also affect how we interpret biosignature searches around other stars. Atmospheric chemistry that seems inconsistent with life based on Earth analogies might actually represent normal geochemical processes in planetary systems with different volatile inventories. Understanding this diversity becomes crucial for avoiding false positives and false negatives in the search for life beyond our solar system. As we continue studying 3I Atlas through its solar passage, each spectrum and measurement adds data points to models of planetary formation that were previously based entirely on theoretical calculations and our own system's limited examples. The story of 3I Atlas represents just the opening chapter of a new era in astronomy, where visitors from other star systems transform from extraordinary rare events into routine subjects for scientific study. As we watch this particular wanderer fade back into interstellar space, the astronomical community is already preparing for an influx of similar objects that will revolutionize our understanding of the galaxy's hidden populations. The Vera Rubin Observatory stands as humanity's primary weapon in this cosmic census. Currently under construction in Chile, this revolutionary facility will begin operations with an 8.4-meter mirror and 3.2 gigapixel camera that will map the entire southern sky every 3 nights. The sensitivity and coverage represent quantum leaps beyond current survey capabilities. Theoretical estimates suggest Rubin might detect anywhere from 1 to 70 interstellar visitors per year, transforming these cosmic accidents from anecdotal curiosities into statistical samples large enough for population studies. We'll finally be able to answer fundamental questions about size distribution, chemical diversity, and origin patterns of debris wandering between stars. The transition from individual case studies to statistical analysis will fundamentally change how we approach interstellar visitor science. Instead of treating each object as a unique mystery, we'll identify correlations and trends, revealing underlying physics. 3-ATLAS, along with Oumuamua and Borisov, will serve as calibration dataset for interpreting much larger populations. The European Space Agency's Comet Interceptor mission represents our most ambitious attempt to study these visitors up close. Launching in 2029, this innovative spacecraft will position itself at L2 Lagrange point, roughly 1.5 million kilometers from Earth, where it will wait in readiness for targets of opportunity that haven't even been discovered yet. When the next suitable interstellar visitor arrives, Comet Interceptor can redirect toward intercept trajectory within months rather than years. The mission acknowledges that preparation must begin before visitors arrive, not after they're discovered. The spacecraft carries instruments designed specifically for high-speed encounters with pristine objects from other star systems. The rapid response frameworks developed for 3-ATLAS provide templates for studying future visitors. The real-time integration of data from space-based and ground-based observatories created unprecedented synergies where each instrument's capabilities complemented the others. This collaborative approach maximized scientific return from brief encounters with fast-moving targets. Target of opportunity. Protocols have evolved from 3-ATLAS experience to allow major facilities to redirect attention within days of discovery. Traditional astronomy operates on yearly planning cycles, but interstellar visitors demand response times measured in weeks. The field has adapted to accommodate these time-critical phenomena. Machine learning algorithms trained on 3-ATLAS data will improve our ability to identify interstellar visitors in the torrent of discoveries that Rubin will produce. Automated systems that can distinguish between solar system natives and extrasolar immigrants will be essential for managing data volumes that next-generation surveys will generate. International cooperation frameworks established during the 3-ATLAS campaign demonstrate how the global astronomical community can coordinate responses to unprecedented phenomena. These collaborative models will prove essential as discovery rates increase and multiple visitors require simultaneous study. Educational institutions have integrated interstellar visitor science into curricula, preparing the next generation of researchers for a future where such objects represent routine rather than exceptional phenomena. Students learning planetary formation theory now study examples from other star systems alongside local analogues. Public engagement strategies developed during 3-ATLAS coverage provide models for communicating complex scientific concepts while maintaining accuracy and avoiding sensationalism. As discovery rates increase, clear science communication will become increasingly important for maintaining rational public discourse about these cosmic messengers. The technological innovations driven by 3-ATLAS studies have accelerated developments in spectroscopy, orbital mechanics, software, and multi-wavelength coordination that benefit the broader astronomical community. These advances will enhance our capability to study not just future interstellar visitors, but small body populations throughout the solar system. As 3-ATLAS fades beyond detection limits, carrying its remaining secrets back to the galactic medium, we're left with knowledge that more visitors are already en route. Somewhere in cosmic darkness, other ancient fragments from distant star systems are following their own trajectories toward our solar system. In the coming years, the night sky will undergo a revolution as profound as any in astronomy history. The Vera Rubin Observatory, nearing completion on a Chilean mountaintop, will transform our understanding of the universe by discovering phenomena at rates dwarfing all previous surveys combined. For interstellar visitor science, Rubin represents nothing less than the transition from accidental discoveries to systematic census-taking of the galaxy's wandering populations. The raw numbers are staggering. Rubin's 8.4-meter mirror and 3.2 gigapixel camera will image the entire visible southern sky every 3 nights, collecting data at rates that would have taken decades using previous generation facilities. In its first year of operation, Rubin will discover more asteroids than have been found in all of human history, combined. Hidden among these solar system natives will be our next interstellar visitors. The sensitivity improvements represent quantum leaps beyond current capabilities. Where ATLAS, the survey that discovered 3I ATLAS, can detect objects down to magnitude 19, Rubin will routinely reach magnitude 24, roughly 100 times fainter. This means finding interstellar visitors much earlier in their approach trajectories, providing months or years of advance warning, instead of rushed few-month campaigns that characterized previous discoveries. Theoretical models suggest Rubin could detect between 1 and 70 interstellar visitors annually, depending on the true size distribution and orbital characteristics of the galactic debris population. Even conservative estimates represent dramatic increases over current discovery rates. The field will evolve from studying individual objects as unique phenomena to analyzing populations large enough for statistical inference. This transition will fundamentally change the questions we can address. Instead of asking whether 3I ATLAS represents typical interstellar chemistry, we'll determine what fraction of visitors show carbon dioxide dominance, rather than speculating about size distributions based on 3 examples. We'll measure them directly across hundreds of objects. Population statistics will replace individual case studies. The early detection capabilities will enable entirely new approaches to interstellar visitor science. With years of advance warning, spacecraft missions could be designed and launched specifically to intercept interesting objects. The European Space Agency's Comet Interceptor mission represents the first step in this direction, but future missions could target specific visitors based on their observed properties during approach. Advanced data processing pipelines will automatically identify interstellar visitors among the millions of moving objects that Rubin detects nightly. Machine learning, algorithms trained on the orbital characteristics of known interstellar objects, will flag candidates for immediate follow-up observations. The human-intensive discovery process that characterized the first 3 visitors will give way to automated detection and classification. The spectroscopic follow-up capabilities needed to characterize Rubin's discoveries will require coordinated responses from observatories worldwide. The James Webb Space Telescope, large ground-based telescopes, and specialized infrared facilities will need to work in concert to extract chemical information from objects that are fainter and more distant than previous interstellar visitors when first detected. Rubin's temporal resolution will reveal how interstellar visitor properties evolve during their passage through the solar system. Rather than snapshot observations that characterize 3I ATLAS studies, we'll track changes in brightness, spectral characteristics, and morphology from discovery through departure. This evolutionary perspective will provide insights into how these objects respond to solar heating and gravitational perturbations. The survey will also detect objects in unusual orbital orientations that might have been missed by previous surveys with more limited sky coverage. Some interstellar visitors might approach from directions that previous facilities couldn't monitor continuously, potentially biasing our understanding of population characteristics. The chemical diversity revealed by larger samples will either confirm that the three known visitors represent typical examples, or reveal that they were unusual outliers in a much more diverse population. If carbon dioxide dominance like 3I-ATLAS proves common, it will revolutionize our understanding of volatile chemistry in other stellar systems. The coordination requirements will challenge traditional astronomical practices. Rubin will discover objects faster than follow-up facilities can characterize them, requiring prioritization schemes that balance scientific interest against observational resources. Not every interstellar visitor will receive the intensive study that characterized 3I-ATLAS. The Rubin revolution will transform interstellar visitors from rare curiosities worthy of global attention into routine subjects for systematic study. This evolution will finally provide statistical samples needed to understand how common worlds like ours are in the galaxy. The space between stars has long been considered empty by human standards, a near-perfect vacuum decorated with the occasional hydrogen atom and grain of interstellar dust. But 3I-ATLAS and its predecessors are forcing us to rewrite this picture entirely. The interstellar medium isn't empty at all. It's filled with a hidden population of wandering worlds and planetary debris that connect star systems across vast galactic distances. Theoretical models have predicted this population for decades. Computer simulations of planetary system formation routinely show that gravitational interactions with giant planets scatter smaller bodies onto hyperbolic trajectories, ejecting them into interstellar space. Every star system should contribute to the galactic debris field through these violent formation processes. But theory and observation are different things. Until Oumuamua's discovery in 2017, these predictions remained untested. The arrival of Borisov in 2019, and now 3I-ATLAS, has provided the first direct evidence that space between stars is indeed populated with wandering fragments from distant worlds. The discovery rate acceleration tells its own story about population density. Improved survey sensitivity has revealed that interstellar visitors arrive more frequently than initial estimates suggested. As detection capabilities improve, we're finding that these objects are neither exceptionally rare nor completely common. They occupy a middle ground, suggesting significant debris populations throughout the local galactic neighborhood. Each visitor has expanded our understanding of what's possible in planetary formation environments. Oumuamua's apparent lack of volatiles, Borisov's carbon monoxide enhancement, and 3I-ATLAS's carbon dioxide dominance represent three distinct formation chemistries within just a few years of observations. This diversity hints at the vast range of conditions that exist around different types of stars. The chemical variety challenges fundamental assumptions about planetary formation uniformity. Our solar system's comet population shows relatively modest compositional variations, suggesting that formation conditions around our Sun were reasonably uniform. But the dramatic differences between interstellar visitors indicate that other stellar systems developed under much more diverse conditions. The size distribution inferences, based on the limited sample, suggest that smaller objects vastly outnumber larger ones, consistent with theoretical predictions, but difficult to verify observationally. The three confirmed visitors span sizes from hundreds of meters to several kilometers, implying an underlying population where objects like 3I-ATLAS represent rare, large examples of a much more numerous population of smaller debris. The survival implications of successful interstellar journeys provide insights into material properties and internal structures that can endure millions of years in the harsh interstellar environment. Cosmic ray bombardment, impacts with interstellar dust, and thermal cycling should gradually erode and alter any object traveling between star systems. The ejection mechanisms that populate interstellar space with debris operate on different timescales and through different processes than our own solar system experienced. High-mass stars evolve more rapidly and experience more violent late-stage evolution that could scatter planetary material across larger volumes. Age estimates for visitors like 3I-ATLAS suggest that some debris has been traveling for billions of years, accumulating from ejection events that occurred throughout galactic history. This means the current interstellar population represents sampling of planetary formation processes across multiple epochs of stellar evolution and galactic chemical enrichment. The density estimates for local interstellar space, based on visitor encounter rates, suggest that every cubic light-year contains thousands of objects larger than a few hundred meters. This population represents a vast reservoir of solid material that connects stellar systems across the galaxy, creating a network of chemical exchange operating on million-year timescales. The exploration implications of ubiquitous interstellar debris suggest that human expansion beyond the solar system might encounter waypoints and resources scattered throughout local space. Rather than crossing completely empty voids, interstellar travelers might find stepping stones of material that could provide raw materials for fuel, construction, or scientific study. As we've learned from 3I-ATLAS and its predecessors, the universe routinely surprises us with phenomena that challenge our assumptions. The interstellar medium isn't the empty vacuum we once imagined. It's a dynamic environment filled with the wandering remnants of planetary formation processes that operate throughout the galaxy. The chemistry of interstellar visitors serves as a cosmic library, where each object carries molecular signatures encoding formation conditions around distant stars. In just 3 confirmed visitors, we've discovered chemical diversity exceeding anything found in our own solar system, suggesting that planetary formation throughout the galaxy produces materials under conditions we've barely begun to imagine. Oumuamua's apparent lack of detectable volatiles represented our first glimpse into how different planetary formation could be elsewhere, whether through formation in an unusually dry environment, complete processing by interstellar radiation, or other mechanisms we don't understand. This visitor challenged assumptions that all small bodies contain substantial ices like their solar system counterparts. Borisov's carbon monoxide enhancement provided the second data point in our growing understanding of chemical diversity. The elevated CO to water ratios suggested formation in environments colder than our own outer solar system, perhaps around a star with more extended regions where carbon monoxide could condense. This chemistry hinted at planetary systems with different thermal architectures than our Sun's domain. Now 3I-ATLAS has delivered the most extreme chemical signature yet observed, carbon dioxide dominance that exceeds anything in our experience by factors of 4 to 8. This composition points to formation near CO2 snowlines in environments where thermodynamic conditions favored carbon-bearing volatiles over the water-dominated chemistry we consider normal. The progression from no detectable volatiles to carbon monoxide excess to carbon dioxide dominance spans a chemical range that our own solar system's comets don't approach. If these 3 visitors represent typical examples rather than extreme outliers, then planetary formation chemistry varies far more dramatically between stellar systems than our local perspective suggested. The implications extend beyond mere compositional curiosity to fundamental questions about atmospheric evolution on planets formed in these diverse environments. A world that accreted from carbon dioxide-rich planetesimals would develop very different atmospheric characteristics than Earth's water-dominated accretion. The isotopic signatures, when they can be measured with sufficient precision, could provide the most definitive evidence for alien formation environments. Carbon and oxygen isotope ratios reflect nuclear processes operating in different types of stars. A carbon dioxide molecule with isotopic characteristics, unlike anything produced in our solar system, would definitively prove formation around a star with different mass, age, or metallicity. The stellar metallicity effects on planetary formation chemistry provide context for understanding the diversity we observe. Stars formed during different epochs of galactic evolution contain different abundances of heavy elements, potentially producing planets and debris with chemistry reflecting these temporal variations. 3. I-ATLAS might represent formation during an era when stellar compositions differed significantly from current conditions. The habitability implications of diverse planetary formation chemistry affect our understanding of where life might emerge throughout the galaxy. Worlds formed from carbon dioxide-rich materials might develop atmospheric compositions that seem hostile by Earth standards, but could support entirely different biochemistries adapted to high CO2 environments. The classification schemes we're developing for interstellar visitor chemistry will expand as detection rates increase and sample sizes grow. The simple categories based on 3 objects: volatile and CO2-dominated MA will evolve into more sophisticated taxonomies that capture the full range of chemical diversity produced by different stellar environments. As detection rates increase and chemical analysis techniques improve, interstellar visitors will become increasingly powerful probes of planetary formation diversity throughout the galaxy. Each new arrival potentially represents sampling a different stellar environment, gradually building a chemical map of how planets form under conditions spanning the full range of stellar masses, ages, and compositions. The chemical diversity we've discovered in just 3 visitors suggests that the galaxy routinely produces worlds through processes that create materials unlike anything in our local experience, expanding our understanding of what's possible in planetary formation across the cosmic range of stellar environments. As 3I-ATLAS fades beyond the detection limits of even our most powerful telescopes, racing back into the cosmic deep from whence it came, astronomers worldwide have turned their attention to a simple question: where is the next one? Statistical models and discovery rate projections suggest that our 4th confirmed interstellar visitor is already en route, following its own ancient trajectory toward an encounter with our solar system that could happen at any moment. The pattern, established by our first 3 visitors, offers tantalizing hints about what we might expect next. Oumuamua arrived in 2017 with its mysterious acceleration and apparent lack of volatiles. Borisov followed in 2019 with elevated carbon monoxide and conventional comet behavior. 3. I-ATLAS appeared in 2025 with carbon dioxide dominance and exotic outgassing patterns. Each visitor has challenged our assumptions in different ways, suggesting that the 4th will likely surprise us with yet another category of behavior. Survey capabilities have improved dramatically since Oumuamua's accidental discovery. The ATLAS system that found 3I-ATLAS represents current generation technology, but next-generation facilities promise even greater sensitivity. The Vera Rubin Observatory will begin operations imminently, with detection capabilities that could identify interstellar visitors years before they reach their closest solar approaches. This extended warning time will revolutionize our approach to interstellar visitor science. Instead of the rushed few-month campaigns that characterized previous discoveries, we'll have years to plan comprehensive observation strategies, coordinate international responses, and potentially launch spacecraft missions designed specifically for intercept trajectories. The European Space Agency's Comet Interceptor mission will be waiting at the L2 Lagrange point when the next suitable target arrives. This pioneering spacecraft represents humanity's first attempt to prepare for interstellar visitors before they're discovered, acknowledging that successful encounters require advanced preparation rather than reactive responses. Chemical prediction models based on stellar population statistics suggest probable compositions for future visitors. If the thick disk origin hypothesis for 3I Atlas proves correct, we might expect additional ancient visitors with chemistry reflecting formation during different epochs of galactic evolution. Alternatively, visitors from younger stellar populations might show composition patterns that more closely resemble solar system materials. The fourth visitor might represent our first detection of a truly small interstellar object, perhaps hundreds rather than thousands of meters across, testing our ability to study fast-moving targets at the resolution limits of current telescopes. Activity pattern predictions, based on diverse behaviors observed in previous visitors, suggest that the fourth might display yet another category of outgassing physics. Detection probability modeling suggests optimal strategies for finding the next interstellar visitor. Sky survey patterns, sensitivity thresholds, and follow-up protocols can be optimized based on lessons learned from previous discoveries. The fourth visitor might be found through systematic searching rather than accidental detection. The waiting period itself provides valuable preparation time for addressing limitations and missed opportunities identified during previous encounters. Improved analysis techniques, better coordination protocols, and enhanced instrumentation can be developed while anticipating the next arrival. Theoretical framework development continues refining our understanding of what interstellar visitors can teach us about planetary formation throughout the galaxy. Each new arrival potentially tests different aspects of formation and evolution models, gradually building a comprehensive picture of how debris moves between stellar systems. Somewhere, in the darkness beyond our solar system, the fourth interstellar visitor continues its journey toward us. It might arrive next year or next decade, carrying chemical messages from another star and challenging our understanding in ways we haven't yet imagined. When it comes, we'll be ready with instruments, protocols, and accumulated wisdom gained from studying its predecessors. The universe keeps sending us these messengers from the deep, each one expanding our cosmic perspective and reminding us that we participate in a galaxy-wide community of worlds connected by the ancient wandering of matter between the stars.